Hey everyone, this video is going to be all about gravity. It is going to cover some of the stuff we talked about in class and kind of expand on some of the stuff we talked about in class as well. So this is going to be all about gravity. So first I want to start with our relevant equations. Relevant equations. Okay. So, of course, the gravity equation or the force of gravity equation that we're used to, and remember, force of gravity is also known as the weight of an object. We can calculate by doing the mass of the object times the gravitational field that it is in. And in class, we talked about how we can calculate that gravitational field, because that gravitational field is going to vary depending upon what planet we're on. And not only that, but like where we are on the planet, right? So that gravitational field is going to depend on G, the universal gravitational constant, the mass of whatever is creating the field. So if we're finding the gravitational field on Earth, that would be the mass of the Earth. We're finding the gravitational field of the sun at a specific location, then that would be the mass of the sun over the distance between the centers squared, right? Remember that R means distance between centers. Okay. Now, gravitational field can be measured in newtons per kilogram or meters per second squared. Both are valid, and we've talked about why before. Okay, and G is on our reference table, 6.67 times 10 to the negative 11 meters cubed over kilogram second squared. Again, don't have to memorize that. It is on our reference table. Okay. Now, every object with mass is going to have a gravitational field around it. So if this is the Earth, the gravitational field around the Earth kind of looks like this. Now, these lines are invisible, but basically what this is showing is how the gravitational field around Earth is going to attract any other mass that we put around Earth. There also exists a gravitational field around us, right? Remember, we calculated that. So around us, our gravitational field kind of looks something like this. And the closer those field lines are together, the stronger the field is. So where those field lines are close together, close to the surface, the gravitational field is pretty strong. Where they're farther apart out here, the gravitational field is going to be weaker. And again, that's because of that R squared. So if I was to combine this force of gravity equation with this gravitational field equation by substituting in, I would get our second force of gravity equation, okay, which is G, mass object, mass field creator, all over the distance between centers squared. So those are all of our relevant equations for gravity. Right? Now, again, one of them we already know, the other two we figured out in class. Okay? Now let's talk about some sticky bits with gravity. And by sticky bits, I mean like things students tend to mess up a lot or some challenging questions. Okay? So this is something that might come up in the concept builders and stuff, but usually they'll say like a planet with radius r has a g on the surface of like, let's say 10. What is the value of g to r from the surface, right, at x? Right, so they might say find g at x. Right, which is 2r from the surface, okay? So what a lot of students will do is they say, all right, well, m over r squared. So if g and m are remaining constant, because the mass of the planet is not changing, that means g is proportional to 1 over r squared. I am at a distance of 2r, so g is proportional to 2 squared. So g changes by a factor of 1/4. So then g is now equal to 2.5 newtons per kilogram. Okay. And while that's a great process, the students are forgetting one thing, right? Is that r represents the distance from the center. So when we're at 2r from the surface, we are actually a grand total distance of 3r from the center. So when we're at the surface, we're a distance r from the center. When we're at x, we're at a distance of 3r from the center. So we actually haven't double r. We instead have actually tripled r. So instead of plugging in a 2, I need to plug in a 3, which means g, instead of changing by a factor of 1/4, changes by a factor of 1/9. Which means if I want to find my new g, I should be doing the original g of 10 newtons per kilogram times the factor change, which is 1/9. And that'll give me my new value for g, which is going to be 1.1 newtons per kilogram, not 2.5. So that's something to pay attention to, right? Is when you have like your 2r from the surface, but remember, r is a distance from the center, right? This is from the center, so we're actually 3r from the center, okay? So make sure you are including the radius plus the height of the orbit in your distance from center, if not already given. Sorry, my pen's being a little weird. Okay. Because that's essentially what we did, right? We included the radius of the planet, r, plus the height of our orbit, 2r, to get our distance from center of 3r. So that's one sticky bit. Okay. Here's another sticky bit. So let's say we're talking, or we're comparing forces of gravity between the Earth and the moon. And we have a student discussing, and the student says, well, the force of gravity on the Earth by the moon is going to be smaller than the force of gravity on the moon by the Earth, because the moon has a smaller mass, so it can't pull as hard on the Earth as the Earth pulls on the moon, right? So they're essentially saying that the Earth pulls harder on the moon than the moon pulls harder on the Earth. So pause the video for a second and think about any drawing errors or any errors in the student's thinking. Why might the student be drawing this? What errors might they be thinking? So pause the video for like 30 seconds or so and think about this. How might you edit this? What might the actual answer be? So I'm going to assume that you actually pause. And there are errors, right? Now you might think maybe the student is correct, but they actually are wrong, right? So conceptually, right? The conceptual reasoning, why they're wrong, right? Newton's third law says that whenever two objects interact with each other, the force created in that interaction is equal and opposite. So what that means is that the force that the Earth exerts on the moon is equal and opposite to the force that the moon exerts on the Earth. So these two force arrows should be completely equal in size because of Newton's third law. Right? So if the force of gravity on the moon by the Earth, let's say, and this is a complete under-exaggeration, is 20 newtons, then the force of gravity on the Earth by the moon is also going to be 20 newtons, right? That's because of Newton's third law. So let's mathematically prove why this is. Okay? So the force of gravity on the Earth by the moon, right? I don't know anything about gravitational field, so I would use the big G equation. So I would do G, mass Earth, mass moon, divided by the distance between the centers squared. The force of gravity on the moon by the Earth, I would do G, mass moon, mass Earth, over the distance between them squared. These two equations are the exact same thing. The only difference is that the order of the masses is different. But we know from math class that when multiplication occurs, the order doesn't matter, right? That's the commutative property, I think. Order doesn't matter. So these two forces of gravity are completely equal to each other. Okay? So we got our conceptual proof that the student was wrong because of Newton's third law, and we got our mathematical proof using the force of gravity equation. So that's just something to pay attention to. Okay, so those are kind of some two sticky bits. So now let's get into how gravity works when it comes to orbital motion. An orbital motion is just a fancy name for the force of gravity as our net centripetal force. Okay. So we can see orbital motion in a couple of different instances. We could see it with a planet orbiting a sun. And in this case, the sun would be the field creator and the planet would be the object. We could see it with a moon orbiting its planet. And in that case, the object would be the moon and the planet would be the field creator. And we can even see it with the Earth and satellites that orbit the Earth. And yes, my satellites kind of look like TIE fighters. And in that case, the Earth is the field creator and the satellite is the object. Now, the pattern that we're seeing is whatever mass is in the center is our field creator. Right, that's the thing that's creating that gravitational field. And then the object is the thing that is doing the circling. So when I'm labeling things mass field creator, mass object, you have that visual there for you. So these are just some basic examples, but they are the pretty common examples. And no matter what example we would be using, all of these things are examples of when we would have a centripetal force. Okay. So here, the net centripetal force acting on the object, doesn't matter which object, would be the force of gravity. Okay? And that would be the force of gravity on the object by the field creator. Okay? And then that would equal the mass of the object. And remember, the centripetal acceleration is v squared over r. Okay? Because that centripetal acceleration changes our direction without changing our speed. This speed here is often called the orbital speed. Right? And remember, this r is the distance between centers. Okay? So it's not this distance here, right? It is this distance, right? So not the green line, but the red line. Right, so it's not like the height above the surface. We want the distance from the center. Okay. Now we have two force of gravity equations. Okay, so we can have mass of object times gravitational field, which is great if we know the gravitational field strength, or the question is asking about gravitational field strength. And then we have the big G force of gravity equation, which is mass object, mass field creator, all over r squared. And again, those could both equal the centripetal force. So we'll kind of take two paths depending upon which force of gravity equation we want to use. So if we want to use the mg equation, we can set m mass of object g equal to mass of object v squared over r. right? We see that the mass of the object cancels. So that could be a planet, a moon, a satellite, whatever is doing the orbiting. And we see that G is equal to V squared over R. Okay. So here's some things about G that can get kind of sticky. Okay. A question could actually ask you for 3 different quantities and be asking you to find the same thing. Okay. A question could ask you to find the gravitational field, and it could be asking you to find G. A question could ask you to find the acceleration due to gravity. I don't know why I put a slant there. Or the free fall acceleration. And it could be asking you to find G. And for orbital motion, as this equation finds, G could also be the centripetal acceleration. Okay? So a question could ask you to find the gravitational field, then ask you to find the acceleration due to gravity, then ask you to find the centripetal acceleration. And you could do all 3 things to find, or the same for each 3 questions, and find the same thing. Okay? So if you had the orbital speed and the radius, you could calculate G that way. But remember, G from the beginning of the video can also be found by doing big G, the mass of the field creator, over R squared. So we could find the gravitational field, the acceleration due to gravity, or the centripetal acceleration doing that way. We could also set that equal to V squared over R, since that is true. Now this is only true for orbital motion. So if you have something that is not orbiting, don't set G equal to V squared over R. Like if something is just accelerating downwards, it's regular acceleration, change in velocity over time. So then we have the other force of gravity equation, G, mass object, mass field creator, all over R squared, is mass object, V, oh no, I got too many M's. Mass object V squared over R, right? So this says the force of gravity is equal to the net centripetal force. Okay. So some things that can cancel left and right. I got a mass object on both sides, right? So basically what we're seeing is that it doesn't really matter what this orbiting object is. That's not going to affect the motion of that orbiting object. So it doesn't matter how big or small the satellite is. The orbital speed, the orbital period, is all going to remain the same. Same thing with like the size of the planet. So even if you were to replace Jupiter and Earth, right, the orbital speed and orbital period would actually remain the same, which is kind of weird. Like if you just swapped their positions, the orbital speed and orbital period would remain the same because these massive objects, the mass of the thing doing the orbiting, would remain the same. It's kind of wild. So the mass of the object cancels, and then one of these distances from center cancels. So we got G, the mass of the field creator, which depending upon the scenario, could be the sun, it could be a planet, it could be the Earth, right? Depends on the scenario, equals V squared. And again, that V squared is that orbital speed. So again, we're seeing our orbital speed really depends on what thing is at the center and how far from that thing are we. Okay. So that orbital speed then can equal G, mass field creator, all over R. Okay? And don't forget, we're still moving in a circle. So our equation for speed in circular motion still holds true. So we could set this radical, the square root, equal to 2 pi r over the period, right? And this is sometimes called the orbital period, right? Which is just the time to complete one rotation in seconds. Okay. So this answer, this t should be in seconds, right? And that's our orbital period. So look, our orbital period should only depend on the mass of whatever is in the center of our circle and how far we are from that, right? All right. So that is just about the end of our video. So to recap, we got our relevant equations. We got our 2 force of gravity equations. right? Our FG is mg, which is great if we know the gravitational field, right? Gravitational field equation, and then our force of gravity equation that has substituted in for gravitational field. Okay? Our sticky bits, make sure that that R is really your distance from center, right? And make sure we're paying attention to some tricky third law questions and not falling into traps that are set up for us. Right? And then we talked about how gravity can be our centripetal force. We can use either force of gravity as our centripetal force, depending upon what information we have or what information we need. Okay? Now, G has a bunch of names, but we can find it all the same way. That's little g, right? So we got a little g and a big G. That's how I often refer to them. Big G being that universal gravitational constant, little g being the gravitational field, the acceleration due to gravity, and if we're orbiting the centripetal, that says for orbit only, for orbit. So if we're orbiting the centripetal acceleration as well. Okay. All right, and that's about the end of this video.